Bismillahirrahmanirrahim. Hello guys, this is Ishan Akbar with a new lecture about foundation engineering. This lecture is about the geostatic vertical stresses in soil mass. From the name of the topic, it is clear that we are going to study the geostatic case. It means that loads are static. We are not going to consider any dynamics in this topic. And the second part of the content or second part of the topic is vertical. It means we will consider only the vertical direction for the calculation of load. And third one is the stress. It means that the units of the calculated stress will be in kilopascals or it will be in pounds per foot scale. So simply, we will move forward and I will let you know the basic concepts about the geostatic vertical stresses. So first of all, we have to know that what the vertical stress is. This is normally in most of the literature books, this vertical stress is denoted by sigma V naught. This is sigma V naught. That it means that vertical static stress. This is vertical static stress. This O means static, means there is zero dynamic load. So it means the stress which is vertical, but the loads are static and nothing is moving. So the definition for this vertical stress, it is the total amount of stress. It is the total amount of stress acting at any point. We will consider any point below the surface of earth. Means if we are going to consider the top level as the surface of earth, then this will be our reference point, or below any other reference point. If the reference point is surface of earth, then we will calculate the stress below the earth's surface. And if there is any other point which we are going to take the reference, so we will calculate the vertical stress below that reference point. So most of the cases, the vertical stress is calculated below the surface of earth. So there are simple rules to calculate the vertical stress or total stress. This vertical stress is also known as total stress or total vertical stress. Total vertical stress. So the rules are simple. The first one is for this stress, for vertical stress, we will not consider the applied loads. For this stress value, applied loads are not considered. We will no need to consider the applied loads that may be point or rectangular or circular loads. But we will not, if they are given in the question and he says to calculate the vertical stress or vertical effective stress, then we will just consider the unit weights of soils and water, etc. But we will not consider the applied loads because applied loads are considered for induced stresses. So the rule number second is effect of water table is not considered. When you are going to calculate the total stress or total vertical stress, you will not consider the effect of water table. You will not see the depth of water table, or you will not consider the location of water table. So the rule number three is just you have to focus on the unit weights of the soils. You may encounter two layers of soil or three layers of soil. So simply you will just ponder on the unit weights of the soils and depths. Simply from the point of interest, you will consider two things: unit weight of soil and depth of that point for which we are going to calculate the vertical stress. To demonstrate this and to make it clear, I have included two examples. The example number one is, we can read this statement: a site is underlain by two layers. So simply we can draw the two layers by without any scale of normally consolidated clay. Yet this normally consolidated means OCR of the soil is 1. The unit weights of the top layer are 19 and 21. This is the top layer. So one unit weight is 19 and other is 21 kilonewton per meter cube, and here this is 21 kilonewton per meter cube. So what is this? Basically, he is giving two unit weights. The first one is the dry unit weight and second one is the saturated unit weight. So for layer 1, this is clay sand. For this soil, the dry unit weight is 19 kilonewton per meter cube. Keep in mind that dry unit weight is always less than saturated unit weight. If he has not mentioned that this is dry or this is saturated, so we can obviously know that the lower value of unit weight given is known as dry and higher value of unit weight is saturated unit weight. The layer is 6 meter deep. So the depth of layer is 6 meter. The unit weights of the bottom layer are 20 and 22. Suppose this is the bottom layer. This is also clay sand. So its unit weight are 20. So lesser value will be considered as gamma D and greater value will be gamma saturated and this is 22 kilonewton per meter cube. So it is 8 meter thick. We'll take the depth of second layer as 8 meter. Below the bottom layer, there lies a bedrock. This is bottom layer, so here bedrock exists. The water table is located 2 meter below the ground surface. So if we move from the ground surface for 2 meters, this will show us the location of groundwater table. And groundwater table is shown by the inverted triangle. So this will show the location of groundwater. So simply, now, point A is located 9 meters underground. Underground means below the ground surface. So we will consider this point as the ground surface and we will move below to a depth of total 9 meters. And this is point A. So determine the vertical stress or total vertical stress at point A. So uh, this point A is located at 9 meter from the top surface of Earth. This is surface of Earth. We can demonstrate it as like this, or we can just draw a tree or the top of the soil. So in these 9 meters, there are three variations. Totally, there are three variations. Mean we can see that from this point to this point means above the water table there is a depth which is 2 meter, so we will call that h1 is equal to 2 meter. And what is gamma for this soil? That is gamma d 19 kilonewton per meter cube. We can see here, if you have drawn the profile according to the given statement, then there will be no need to worry about the arrangements. Simply, this is 2 meter, and here the unit weight for the top 2 meter, because above water table soil is dry, so the unit weight will be 19. So gamma D is equal to, and we can say this as gamma D1, that dry unit weight of first layer. So now next is the same layer but in the saturated zone. Below the water table, the soil will be saturated. So what is depth of this soil? This will be total 6 meter. This one minus this top 2 meters, that is dry zone. So H2 will be equal to 6 minus 2 equals 4 meter. So gamma S1 saturated soil, because the soil below the groundwater is considered to be saturated, and from this point to end of the first layer the saturated unit weight is 21 kilonewton per meter cube. Now moving towards the next layer, we can see here that water table is within the first layer. So this whole soils below this water table will be considered as saturated. So we will ignore this unit weight and we will use this unit weight gamma saturated. What will be H3 here? The H3 is depth from this point to point A. So total depth is 9 meters. And if we subtract this layer from whole distance means 9 meters minus 6 meters. 9 minus 6 is equal to 3 meters, and gamma S2 will be equal to 22 kilonewton per meter cube. So simply, now we have reached point A. So we have to calculate total stress sigma V naught. This will be equal to H1 gamma D1 plus H2 gamma S1 plus H3 gamma S2. And if we multiply the values, we'll simply get the answer. H1 is 2 and this is 19. H2 is 4 times gamma S1 is 21 plus H3 is 3 times 22. If we calculate the answer by using calculator, so the final answer will be 188. So the total stress is 188. Now the next question is, what will be unit? So simply you can see this is kilonewton per meter cube and this is meter. So we will multiply and gamma with H. H is in meters and gamma is in kilonewton per meter cube. So this meter will be cancelled with this one and here it will be square. So the unit will be kilonewton per meter square, or Newton per meter square is known as Pascal. You can say that Newton per meter square is Pascal. So we can write that this is 188 kilo pascals. This is the answer. So sigma V naught is equal to 188 kilo pascals. This is the answer for this question, for this example, that we have calculated the total stress below two soil profiles at a depth of, at any depth, at point A, which is 9 meter below the ground surface. So the example 2 is similar question, but here we have to calculate the total stress for point A, B, C, and D in the figure. This figure is given at point A. You can see this is point A. You can see the point A is located at the ground surface. This is ground surface. So simply what will we do? We will just consider that point A is up on the ground surface. So there is no topsoil over this point. So the total stress simply will be equal to 0 for point A. So we'll write it as sigma V naught at A will be equal to 0. Now, what will be total stress at B? Now, see, B is 3 meter deep from the top surface and there is no water table involved. So, dry unit weight will be used. So, gamma dry is equal to 16.5. So, we'll use sigma V naught B will be equal to H1 gamma D. This is gamma D and this is H1, or you can see this as HB. So HB here is 3 meter, this one from top surface to point B, and gamma D is 16.5 kilonewton per meter cube. When we multiply 16.5 with 3, this will be 49.5. So unit will be kilopascals. Now, we can say that sigma V naught B is equal to 49.5 kilopascals. So now, moving towards point C, because we have to calculate the total stress for A, B, C, and D. For C, we will consider C. You can see here, C, this is point C. For C, water table is located just below the sea. You can see here the water table is, or you can say that water table is located at sea. So there will be no effect of water table, or there will be no saturated soil above point, because we have to see the soil above this point. So at this point there is no saturated soil. So we can say that the soil is single layer. So what is total depth of sea from the top surface? Always you will consider the depth from the top surface. You will not consider it from B or any other point. You will consider the depth from this to point of interest. So here the point of interest is C, and total depth will be this 3 and this 3. So sigma V naught C will be equal to HC, means depth of soil above C, times gamma D, unit weight of soil above sea. So HC is 6 meters and unit weight of soil is 16.5 kilonewton per meter cube. So sigma V naught C will be equal to 99 kilopascals. So this is stress at point C. So for D, we'll move in the same pattern for point D, but we can see that there is another change when we move towards D. This is location of D, and we can see that this D is below the water table. The C was aligned with the water table, but D is below the water table. So we will consider the unit weight of soil as saturated. So this is dry sand, upper layer is dry sand and lower layer is clay. So simply we can say that sigma V naught D is equal to stress for this soil layer. This will be HC gamma D plus this depth till D from C, because we have considered this top depth. Now we will take this depth from C to D, and C to D, that is 13 meter. We'll write it as H. You can take it as H, or you can simply say that H times gamma saturated. So HC is here 6 meters times 16.5, this 6 meter and this 16.5 plus 13 times 19.25. We have calculated this as 99, and we have calculated this one 19.25 times 13, and the answer will be sigma V naught D is equal to 349.25, and the unit of stress will be kilopascals. This is the total stress, or these examples illustrate the total calculation of total stress at any point or for any point below the surface of Earth. So the next topic or next content of this lecture is the pore water pressure. So what is pore water pressure and how can we calculate? So pore water pressure is the total amount of stress acting upward. Vertical stress acts downward, but pore water pressure resists this stress and this acts downward. So you can say that this is U naught and this is sigma V naught, acting upward due to amount of water present above any point of interest. We can consider the point of interest, or you can say that this pore water pressure will be the pressure due to water present. For point D, the pore water pressure will be result in the pressure from this line to this line. It means that water of 13-meter depth will exert a pore water pressure for point D. There will be zero pore water pressure for point C because there is no water above C. There will be zero pore water pressure for B because there is no water above B, and there is no pore water pressure for A because there is no water above A. For pore water pressure to be considered, it must be present above the point, but not below the point. We will consider only the water present above the point for pore water pressure calculations. So the rules for this are simple, that we will not consider the applied loads, but depth of water table must be known. In these questions, if depth of water table is not known, there will be a little bit of problem. But in such case, or to calculate pore water pressure, we must know the depth of water table. So the third rule is the unit weight of water, and it is 9.81 for in SI unit system, and 62.4 lb per foot cube for PSF, pounds second fit system. So this example 3 illustrate the calculation of pore water pressure. So I have included the same question as we did the example 1. We can draw the profile by keeping in mind the previous given data as we did in question 1. This was 6 meters thick, this was 8 meter thick, and point A was located 9 meters below the surface of soil. This is point A. Now we have to, this pore water pressure is considered or denoted by U and not means static. So we are just considering the geostatic position, that soil is not moving or there is no load on the soil surface. So first unit weight is 19 and the other one is 21. So here the first unit weight is 20 and the saturated is 22. Water table was located at 2 meter below the surface of soil. So now we have to calculate the pore water pressure for point A. What will be pore water pressure for point A? It will be the pressure of water above this point. So we can see that water is disturbing this A from this point to this point. So simply we will calculate the height of water table from this point of interest. Here this point of interest is A. So see, pore water pressure for point A. So we will see the depth of water table above A. So what is total depth of A? We will see this HW. We will write it as HW. So the total depth is 9 meters from the topsoil, and this water table is 2 meters. So simply the depth of water above point A will be equal to 7 meters, because we are considering meter units and Newton units. So it is SI system. So in SI system, unit weight of water is 9.81 kilonewton per meter cube. So U naught will be equal to, or U naught A will be equal to HW gamma W for this point A, and HW is 7 meters and gamma W is 9.81 kilonewton per meter cube. So simply the answer will be 68.67. So this is also stress. Its unit will be kilopascals. U naught A. This is geostatic pore water pressure for point A or above point A. This is example 4 to calculate the pore water pressure. For the same example number 2, there we calculated the whole total stress. So simply see the water, there is no water above this point, so UA will be equal to 0. You can see that there is no water above this point, so pore water pressure for B will be equal to 0. There is no water above C, so pore water pressure for C will be equal to 0. So what will be mu D? UD. This will be simply the depth of water above D. So this is water table. What is depth of D from C? This is 13 meter. So we will write 13 meters time unit weight of water. This is SI system. So unit weight of water is 9.81 kilonewton per meter cube. So for simplifications, mostly authors use gamma W equal to 10 kilonewton per meter cube. So here it will be 13 times 9.81, 127 point. So this is 127.53 kilopascals. This is pore water pressure is also a stress. So now the topic is vertical effective stress. There we and first we studied the effective stress or total effective stress, but here it is sorry, vertical stress or total vertical stress, but here we have used the word as effective. So simply we can see that sigma dash V naught, So effective stress is sigma dash V naught. Total stress is sigma V naught, and effective stress is U denoted by sigma dash V naught, and this will be equal to sigma V naught. We calculated in example 1 and 2 minus U naught. We calculated in example 3 and 4 for both examples. So simply, if we have sigma V naught, total stress of 100, and there is U naught of 50, then effective stress will be equal to 50 kilopascals. So simply, we have got rules for this. Also, we will not consider the applied loads. Sorry. Second one is water table is considered, effect of water table is considered, and unit weight of soils and depth are considered with the unit weight of water. First example is same as example 1 and 3. So we have calculated, simply we can say that sigma dash V naught is equal to sigma V naught minus U naught for point A. So we calculated sigma V naught for point A as 188. I will show you, and go here. Example 1. You can see here that we calculated sigma V naught for this question as 188. And what is U naught for this question? U naught for this question is this one, 68.67. 68.67. So we will simply put the value 68.67, and sigma dash V naught will be equal to 188 minus 68.67. This is 119.33 kilopascals. This is the n- vertical effective stress or net effective stress, because in its definition there is a word of net effective stress. Net means we have to uh, subtract the effect of pore water pressure from the total stress calculated. And in next example 6, you can see that we have to calculate the vertical effective stress for point A, B, and D, C, and D. So for A, vertical effective stress will be equal to total effective stress, because UA is 0. There is no effect of uh, pore water pressure. So sigma dash V naught B will be equal to sigma V naught B, because pore water pressure for B is 0, and for this was 49.5, and this is 0. And sigma dash V naught C, for C total effective vertical stress is same, because there is no water pressure. V naught C, that was 99 kilopascals. This is 49.5 kilopascals. And for sigma dash V naught D, this is sigma V naught D minus U D, or U naught D. And total stress for point D was calculated to be, you can see here, 127, sorry, total stress, total vertical stress was 394.25. So we'll write here as 3, sorry, I will calculate it again. This is 349 point, yes, right. And the pore water pressure is 13 times 9.81, as we calculated 127.53, and the difference will be effective vertical stress at point D. And if we calculate the difference for these two values, that will be 221.72 kilopascals. So for point A, the vertical effective stress is 0, because total stress was 0. For B, the vertical effective stress is equal to total stress, because pore pressure is 0. And for C, the vertical effective stress is equal to total stress, because the pore pressure is 0 for point C. And for D, it is total effective stress, total stress, or total vertical stress subtracted uh, or minus pore pressure at point D. So the total effective vertical stress at point D will be 221.72. This was all about this lecture. Thank you very much. If you like my videos, recommend to your friends and take care. Allah Hafiz.